Good morning, everybody. My talk is actually closely related to the previous one. Stanislav reported the experimental observation of dipolar dynamics in classical relaxer lead magnesium niobate, and my talk is about the theoretical studies. Thus, I can skip a lot of introduction, and I can say only that relaxers are known to be very complex materials which are very hard to study, and especially because if we're talking about relaxer ferroelectrics, this means that electrics according to their name. And a ferroelectric phase appears at some temperature, which is associated with some lattice mode softening, some dipolar dynamic freezing, and to understand what happens, we need to understand the dipolar dynamics. And it is very hard to measure the dipolar dynamics in relaxers at the terahertz and around range. And here I show the picture borrowed from this recent paper, which summarize all the most important investigations, experimental investigations, and shows the frequencies of low-lying optical transverse lattice modes. And you see that the points are everywhere. Thus, all the space of temperature and frequencies are filled by experimental points almost homogeneously. Thus, and many experimental techniques like inelastic Newton scattering, Raman scattering, and infrared techniques, they measure the properties only in some particular intervals of frequencies, temperatures, and so on. Thus, the situation is interesting. Usually, experiment is used to verify the theory. Here we can use the theory to verify experiment and to choose which experimental data fit better the real situation. Our work is based on these two ones. Recently, we published the molecular dynamics, first principle-based molecular dynamics simulations in lead-free relaxer, BZT, but the behavior there is known to be very different as compared to classical PMN relaxer. We apply the same molecular dynamic technique for PMN. Of course, we need different model Hamiltonian, and we use this Hamiltonian from this recently published paper for PMN, but they apply Monte Carlo simulations. But the Hamiltonian we used was exactly the same. And this is briefly the review of approach. It's quite general. We have the Hamiltonian considered two contributions, the average contribution, and the second one, local contribution, which is related to the disorder in the arrangement of magnesium and niobium cations over the lattice sites. We use the supercell of 18 by 18 perovskite unit cells and simulations at about 50 different temperatures in the range between 1,000 and 10K. And then we calculated the time dependence of the dipole moment of the supercell. And then, using this formula, we calculated a real and imaginary part of electric susceptibility. This is the example of what we have at some particular temperature, 150 degrees. These are the frequency dependencies of real and imaginary part of susceptibility. You can see clearly two lattice modes. They are here at 1 and 2 with negative real susceptibility and 1 relaxation at lower temperatures. And this figure looks like experimental data, and we treated the results as experimental results. Thus, we use simple models. In this particular case, this is the model of damped harmonic oscillator, and each mode was described by one oscillator, and the relaxation is described by Haverlach-Negami equation, which is most general relaxation equation. You see the fitting is quite good everywhere except very high frequencies. This is the usual and known problem when the relaxation and oscillation frequencies are close. It is hard to describe them simultaneously. Thus, we use this general model, which combines two coupled oscillator relaxators. Each term contains the contribution of oscillations and relaxations, and sometimes this equation, it depends on our aim, which part of the relaxation spectrum we fit. And these are the results. Thus, we calculated the relaxation and oscillation parameter at every temperature, and then we can calculate the temperature dependence of the susceptibility. It's quite familiar picture. The maximum of a real part of susceptibility increases with frequency, as it should be in relaxers. And this is the quantitative figure. Now let's compare this data with experiment. Here you can see dashed lines are experiments from these papers, and solid lines simulations. The same color corresponds to the same frequency, and you can see that at high frequency, the correspondence between experiment and calculations is very good, especially at above 500. See, at low frequency, the correspondence is not so good. It's clear because we cannot simulate very low frequency. We need very long time for simulations. And these are the results concerning the four-known modes. We observe two four-known modes. One of this mode, nu 1, softens on cooling and then almost frequency independent, and the second one appears below about 350 K. And now, if we compare our results, which are shown by solid black line with triangles, with experiment, we can see that in experiment we can find in any temperature frequency range good correspondence. I will talk about this a little bit later. What is important, this is the mode plasma frequency which we calculated for our low-lying mode, and our calculations fit very well to the experimental data found for last mode, which is known to be often ferroelectrically active in lead-containing perovskites. Thus, we simulate in practice lattice mode, and this is the soft mode. I will show it later. And what about the relation between experiment and calculations concerning the relaxation, low frequencies? This is the calculated relaxation frequency. It follows Arrhenius law with the parameters shown. And if we compare this with experiment, you have already seen this figure in the previous talk, we can see they found experimentally also one of the modes follows the Arrhenius law. The parameters are a little bit different, which is understandable between we study different frequency intervals. And what is important, there is no experimental data above 500 K. It's impossible to measure, very hard to measure. We have the access to all temperatures, and these slides show the contribution to the total static susceptibility of phonons and relaxations. And you can see that relaxation appears above 500 Kelvin. Above this temperature, this first term in the expression for the total susceptibility vanishes. And we know that 500 K is the temperature where the well-known now T-star temperature is observed. It corresponds to the anomaly in the temperature dependence of lattice parameter. It corresponds to the acoustic emission anomaly, just above 500. But I need to say that this temperature, T-star temperature, according to different experiments, find little bit different temperatures, and we try to show that there are two T-star temperature according to our simulations. They are different, and this is another comparison with experiment. This is the dynamic component of quasi-elastic diffuse scattering, and if we fit our relaxational contribution, we see that the shape is very similar. Dashed line is the calculations, and circles are experiment. If we are thinking how to explain our observation with some simple model, we can suggest the following. If this is the potential relief at high temperature above Burns temperature, we observe only vibrations. And the response can be described by a single underdamped harmonic oscillator. Below B temperature, TB temperature, Burns temperature, we observe overdamping, and this could be described as the change of potential relief and harmonic vibrations. And below T-star temperature, we observe the emergence of relaxation. Thus, we have relaxation plus harmonic vibrations due to phonons. And interestingly, this picture corresponds exactly the probability density function found some time ago by our chairman in PMN when he studied neutron scattering. And this is the distribution of lead ions. Maximum of probability density function corresponds to the minimum of the potential. Thus, again, the figure from the paper, the shifts of lead ions from the centrosymmetric position vanishes at Burns temperature, and it looks like phase transition. But experimentally, it is not possible to determine if these displacements are static or dynamic. Thus, it could be that these are just frozen displacement of lead ions due to, for example, compositional disorder. But according to our data, we see that these are the dynamic displacements of lead cation from the centrosymmetric position, and it looks like really phase transition from high temperature cubic phase. And this transition is of second order, and this is the critical exponent, 0.31. And the change of properties observed experimentally at this Burns temperature could be explained in the following way. You know that original Burns picture is that at Burns temperature, polar non-origins appear. This means that the dipole moment, dynamic dipole moment of different unit cells become ordered in some non-origins, and this leads to anomaly and temperature dependence of reflective index due to electro-optic effect. But in our picture, we have the same, but on the scale of single unit cell. The dipole moment appears at every unit cell, and this gives rise to the anomaly of refractive index, volume, and dielectric permittivity, as I show below. Now let's compare more closely the results, the high-frequency results. Our data are close very well to the data of hyper-Raman scattering, light scattering. The simulations, you see in simulations, the softening of this mode according to the Cochrane law, and the same we observe in experiment. Interestingly, the high-frequency mode, which is observed again below 350 K, follows another Cochrane law with a different critical temperature, and this experimentally observed critical temperature is very close to our simulations. And frequency, you see, are very close to one another. Thus, one again important point is that below Burn's temperature, the mode, this phonon mode becomes overdamped according to experiment and according to our simulations. Thus, this means that in the interval between 200 and say 600, it cannot be measured reliably. But in our simulations, we can find the temperature dependence. And if we look at the temperature dependence of this soft mode, nu square is the crosses, and the symbols are the reciprocal susceptibility. We see very good Curie-Weiss law at high temperatures, and very good Cochrane law, which completely corresponds to the Curie-Weiss law. And the Curie-Weiss temperature is very close, and Curie-Weiss parameter are very close to the experimental results for Curie-Weiss law. And below the T-star temperature, we observe the second Curie-Weiss law and the second Cochrane law. Second Curie-Weiss law has been reported experimentally with the same parameters in this paper. Second Cochrane law couldn't be observed because the frequency temperature range is unavailable for experiment. But Curie-Weiss law and Cochrane law are the hallmarks for displacive ferroelectric phase transition. We can say that this looks like displacive local ferroelectric phase transition at temperature T-star 350, and that is why we introduce this temperature as new characteristic temperature in PMN and designated it as TC star to distinguish it from T-star and Curie temperature observed at Polt crystal and 210 K. But if it is phase transition, local phase transition, spontaneous polarization should appear at polar nanoregions or polar nanodomains, and this should give rise to the lowering of symmetry as described in the previous presentation. And what we did, we calculated the response inside the polar nanoregions. We used the polar nanoregions of about 30 unit cells, perovskite unit cells, and calculate the response perpendicular and parallel to spontaneous polarization inside this polar nanoregion, and see that high frequency mode is exactly the fluctuations along local polarizations, and this mode is the fluctuation perpendicular to local polarization. And these are some experimental results showing that something happens at this TC star temperature 350 from different experimental data. These are all experimental data, and everywhere you can see that the anomaly exists at this temperature. But what happens at lower temperature, This is the results of previous Monte Carlo simulations. And finally, what is our conclusions? We can derive from our simulations the following sequence of critical temperatures in PMN, and we can describe these temperatures and explain them. Thank you for your attention.
One short question.
Thank you for a nice talk. Still puzzling is of this behavior above Barron's temperature. Is there one mode or two modes? You calculate, you obtain one mode, but you calculate polar phonons, or I mean phonons which contribute to permittivity. But in hyper-Raman scattering, there is a second mode which is finally as well polar due to coupling. So can you somehow include coupling in your model? I cannot say that there is only one mode. Maybe yes, but the second mode, higher frequency mode, exists in neutron scattering, and coupling plays the role.
Thus, what about this mode, the third mode, at intermediate frequencies? According to one of your explanations, this is the mode related to the chemical ordering. We cannot observe this mode because our model is completely disordered.
Okay.
What is observed above Barron's temperature, we observe in this case only one mode. The second mode
Speaker again.